Today, we will discuss a power supply design which uses simple diodes and capacitor to convert the alternating current into direct current. In our daily life, we use two types of electric currents: alternating current, which periodically reverses direction, and direct current, which flows in only one direction. In the modern era, almost every household electronics works on direct current, but we get alternating current from power generation plants via transmission lines because AC can be transmitted more efficiently than DC in lower cost. Since our main electric source is AC and some of our devices require DC, we need device to convert AC to DC. For example, this small black box, we connect our laptop to the electric supply to charge it. This is actually an AC to DC converter. To better understand, let's define what a power supply is. A power supply is a device that delivers electric power to one or several load. We generate the output power by converting input signal into output signal. In designing a power supply, we must know the components that we are going to use. To better project the design, this is a block diagram of a DC power supply. Our block diagram consists of four main sub-blocks, namely the transformer, the rectifier circuit, the filter, and the regulator. Now, let's apply the block diagram by making a schematic circuit using Multisim. First, we will need an AC power supply. Depending on your country, AC coming to your home has different voltage level. Here in the Philippines, we use 220 volts 60 Hz. Then we will apply the first sub-block, which is data transformer. A transformer is a device that is used to step up or step down the AC voltage level, keeping the input and output power the same. Next is the rectifier. A rectifier circuit is the combination of diodes arranged in such a manner that converts AC into DC voltage. Basically, there are two types of rectifier circuits, the half-wave and the full-wave rectifier. In this design, we will use a center-topped full-wave rectifier because it is more power efficient than the half-wave. The rectifier circuit converts the incoming AC to DC, but unluckily, it does not make it a pure DC. The output of a rectifier is pulsating DC and is not considered good to power up sensitive devices. The rectified DC is not very clean and has ripples, so we need a capacitor filter to convert a pulsating DC into pure or to remove distortion from signal. A regulator can be in a form of integrated circuit or a diode, and it is used to give a constant output voltage regardless of input voltage changes. Our last main block is the regulator. A regulator is used to provide a regulated constant output voltage. Voltage regulation is very important because we do not need a change in output voltage when the load changes. An output voltage independent of the load is always required. In this circuit, I use 1N4733A Zener diode with the value of voltage 5.1 volts and a power of 500 milliwatts, which will give me a current of 98 milliampere. I use this diode because my desired DC voltage output is 5.1 volts. Now that we completed the four sub-blocks of the diagram, we will now connect all the components and change the values. Here, I use an oscilloscope to see the waveform output signal of my circuit. I also use a probe to check if I achieve my desired DC output voltage, which is 5.1 volts. As I start the simulation, you can see in the probe that My DC output voltage is 5.1 volts. This is the waveform signal of the circuit. The red represents the input and the blue for the output. We can clearly see how it converts the AC signal into DC. Now that we are done doing our circuit diagram, we will now convert it into a printed circuit board. I used easyeda to convert my circuit diagram into a PCB. Before we can make our PCB, we must first draw the schematic diagram of our circuit. I used the library on the left tab to find the components I need for my circuit. After gathering all the components I needed, I now connect all the components based on the circuit we made earlier. Now that we are done doing our schematic diagram, we can now convert it into a PCB. In my PCB design, I use a small PCB because using a smaller PCB can give us an advantages like it is much lower in cost and it can save spaces. Also, it is more environmentally friendly because fewer materials are used in the productions of smaller circuit boards. After arranging the components, I now connect them using the wire. And after that, we're done doing our PCB. That is how we design a power supply. I hope that you learned something from our discussion. If you want to make your own power supply design, just remember the block diagram I showed earlier. And that's it. Thank you for listening.